Oh, hey there. Didn't see you there. So today, we're going to be describing this atom within that magnetic field. Seems daunting, but we're going to do it. So to do this, we have our Hamiltonian here. And to consider within this Hamiltonian is our nuclear spin and total angular momentum, as well as our magnetic field, but we don't actually have to consider the nuclear spin on the magnetic field because that is a very small number, and we're dealing with small numbers, but this is really small, super small. So within our Hamiltonian here, we have these interactions, and to simplify this, our GL and GS, we have to use Landé G-factors approximation to get this here GJ. So then we can then use J equals L plus S and have this new Hamiltonian where we can take our perturbations and get closer to the actual transitions, the allowed ones. So within our 2p 1/2 states, we have L, S, J, M, J, I, M, I quantum numbers, which not always can be good because our MJ is always changing due to the magnetic field in the direction of Z. And so when B naught equals 0, we do have good quantum numbers, but when it is non-zero, like I said, it's changing those values. And so to find our 4 product states, we will now use our total electronic angular momentum, F equals I plus J.
After we calculate our product states, we're going to set up our degenerate subspace matrix to find our first order corrections to those energies. So to do this, we'll set up a matrix and then take the sandwich of our Hamiltonian, this, with our different states. And we'll go through all the combinations of sandwiching to set up our matrix. Then once we'll go in and calculate all those sandwiches to get us our first order correction. So now we have here, we have our first order corrections for those states. And then so here we'll treat this term, we'll use this approximation to simplify this, so the math is a little bit easier to do. And then in that approximation, this term, the square root of the term, will go to 0 when B naught is a lot smaller than A over mu B.
So we only use this approximation when the magnetic field is weak enough. And here we're going to look at the 3 upper energy states here. And the transition, the difference in the energy between these transitions is 1/3 mu B of B naught. To transition between these energy states, you're going to excite it using the electromagnetic waves. And you can see here that the energy of a photon is going to be 1/3 mu B naught or 2/3 mu B naught, which is the same as the amount of energy that it takes to transition between these when you're going down or up in an energy state, so losing or gaining a photon. These transitions are not allowed by the electric dipole transitions because they don't follow the selection rules. And the electric dipole transitions are the most probable ones, which means that these are not probable energy transitions. However, it is allowed by the magnetic dipole transitions, which are far less probable but do allow it to happen. So even though it is a small chance, it is a chance. And you're going to be using Fermi's golden rule for these. So that's what this final to initial state is as it moves between these as it transitions between these energy states. This H1 is going to be our Hamiltonian with our operators. So your operators are going to act on these kets. And those are going to be how you're going to find the whether or not it's allowed by your selection rules.
And that's quantum mechanics. I didn't see you there.